Okay, so today we are going to cover probability. We are going to see geometric probability in section 4. So here is what probability is. Okay, so geometric probability in general is the likelihood that an event will occur. Probability is usually a number between 0 and 1. And you can write it as a fraction, as a decimal, or as a percent. And when you are asked a question to find the answer to a probability question, you're going to see it as the probability of an event A is written as P, and then parentheses with a capital A, and then close parentheses. So whatever event you're looking to happen, that's what's in here. So when your probability is 0, you know it's not going to happen. It's impossible. But when your probability, and that would be like a 0%. If it's 1 or 100%, then you know that's a sure thing. It's for certain that it's going to happen. So the closer your probability is to 0, the less likely it's going to happen. The closer to 1, more likely it's going to happen. You could sort of think of this as like rain. Okay, if they say that there is an 80% chance of rain today, you know that there's a pretty good chance it's going to rain. Or if they say 100%, like a hurricane's coming, you know that for sure it's going to rain that day. And then if it's right in the middle, 50%, then it's equally likely as unlikely to occur, 50-50. Okay, next. Okay, so for the geometric probability, it's going to be a ratio that involves geometric measure, such as length or area. So in this lesson, we're talking about shapes, okay? It could be triangles or rectangles. It could also be segments. So this lesson is all based on shapes. When we get to chapter 12:1, that's when we're going to be talking about like flipping a coin or rolling a dice or picking a card. But in this lesson, it's all about shapes. Next slide. So here would be an example of a geometric probability where we're dealing with length. So it tells us here to let AB be a segment that contains the segment CD. So AB is the whole thing, and CD is just a portion of it. It's there in blue. If a point K on AB is chosen at random, then the probability that is on CD is the ratio of the length of CD to the length of AB. So what I'm stating here is if I'm saying what is the probability that K is on CD, then what I'm looking for is what I'm aiming for. So what I'm aiming for over the whole thing. So for example, for this one, when I was looking for CD versus AB. So CD was what I was looking for, a point on CD versus the whole thing. If I said, what is the probability that K is on DB, then you would do the length of DB over AB. If it said, what was the probability of K being on AB, then you know for sure it's on there because it's AB over AB, and that would be 1 or 100%. Now we don't have numbers here, but we could have numbers and then you would simplify it. So probability that K is on CD, so you're going to do the length of CD over the length of AB. Next we're going to talk about probability in area. So let J be a region that contains region M. If a point K is in J, if a point K in J is chosen at random, then the probability that it is in region M is the ratio of the area of M to the area of J. So you put whatever number you would calculate for the area of M over the area of J. Now you're not going to get strange figures like this. You're going to get triangles or rectangles or squares, something that we actually could calculate the area for. So we're going to probably be given squares or circles or rectangles, something that we know the formula for. So you're doing the area of that pinkish M over the area of the whole J quadrilateral. Everybody good on this slide? Okay. Next, now we're going to go back to the segment. So it says, suppose a point P on segment AF is picked at random. What is the probability that P is on segment CF? So what we're trying to do here is find the length of CF over the length of AF. Okay, so what you're aiming for, so P is going to be on CF over the whole thing. Now, we don't have any numbers here, but we do have this statement here saying that each one of these are congruent. So this is congruent to this. So we could see that CF is actually made up of 3 pieces. So if I go from point C to D to E to F, it's got 3 parts. And then I can also see that the whole thing from A to B to C to D to E to F, the whole thing has 5 parts. So the probability of P being on CF would be 3/5. On the previous slide, we saw that probability could be expressed as a fraction, as a decimal, so you divide it, or as a percent. So 3 ways to write a probability. At a carnival game, dishes are positioned on a table so that they do not overlap. You win a prize if you throw a nickel that lands on a dish. If the area of the table is 1.5 meters squared and the combined area of the dishes is 1 meter squared, what is the probability that the nickel will not land on a dish? So let me give you a little visual. So let's say this is our table, and let's say we have our dishes, and they said that they do not overlap, and they're on the table. It told us that if we throw a nickel and it lands on a plate, so in this blue shaded area, we would win a prize. So it wants us to know what's the probability that the nickel's not gonna land on a dish. So what I can do here is, let me just show you the probability if it did land on the dish. So just change up the problem a little first. We would do the area of the dishes over the area of the whole table, the whole thing. So we knew the area of the dishes was 1.0. We knew that the area of the table was 1.5. Now, I can't leave a decimal in my fraction, so I need to get rid of it. I can either divide this, make it a decimal, and then convert it back, or I can multiply the numerator and the denominator by 10, or just move my decimal point once in the top, once in the bottom, make it 10 over 15, which simplifies to 2/3. So this would be the probability of it landing in the dish. But the question said not landing in the dish. So if I know the total area of the table is 1.5 and the dishes are taking up 1 meter squared, I could subtract it. So the area that's not the dishes so not dishes, over the whole thing would be 0.5 over 1.5. And then I would simplify that. So I can move it once, and I have 5 over 15, and it gives me 1/3. Now, always remember that the event occurring and not occurring needs to equal 1. So if you did this one first, you could subtract it from 1 to get what would be not hitting the dish. So this is the answer that the slide was asking for, was 1/3. If your answer turns into a repeating decimal when you try to divide it, just leave it the fraction. If I were to turn this into a decimal, it would be 0.3 repeating. So I'm just going to leave it in fraction form for this answer. Okay, last slide. Okay, we're throwing a dart. A dart lands at a random point on the square dartboard shown. What is the probability that the dart is within the outer circle? And then the second question, within the bullseye. So I actually have to do 2 questions here. I'm actually going to change this, and I'm going to say just leave it in terms of pi. Okay, so we need to know the formula for area of a circle, and that's going to be pi r squared. So the first thing I need to do is figure out the area of the outer circle. Now, the outer circle is going to be, let's see. First let's do the bullseye first. I think that'll be easier. Let's answer this part first. We're going to do the bullseye first, which is the yellow circle. We can see that the yellow circle has a radius of 1. So remember, we're going to do area of the yellow circle and then we're going to put it over the whole square. So the area of the inner circle is going to be pi r squared, and our radius is 1, so it's going to be pi over 10 times 10, which is 100. So if it said leave in terms of pi, this would be the answer to the dart landing within the bullseye. Now, if it didn't say that, then you would put 3.14 in there and then move the decimal point and simplify. But we're leaving it in terms of pi, so that's the answer for the bullseye. Now, for the outer circle, what I need to do here is find the area of the blue circle. Okay, I don't want it landing in the bullseye, so I'm going to find the area of the entire blue circle and then subtract out the bullseye circle. So for this part of the question, let me do this one in blue. I'm going to find the area of the whole circle, and then I'm going to subtract the yellow circle. So area of the yellow to get just that outer blue area. And then once I get those 2 numbers, then I put it over the whole square. So the area of the whole circle, notice that the blue part right here is 4, and then again, the yellow circle has a radius of 1. So I'm dealing with the whole circle has a radius of 5. So I'm going to do pi r squared. So the whole circle is going to be 25 pi minus the yellow circle, which is 1 pi, over the 10 times 10. I'm going to subtract 25 minus 1 and get 24 pi over 100. I can reduce 24 over 100. I can divide them both by 4 and get 6 pi over 25. And these would be units squared, or just no units. We'll just leave it. It's a probability. Okay, so 6 pi over 25. And that is the geometric probability. So your homework for this lesson is 11 for practice B. And now we're going to cover the other probability from chapter 12. So everyone look for your 12-1 notes.